So today we are going to start today's class by looking at the report, the manager report from the ADU we worked on the former class, in the last class rather. So the address, you can see all the information is stated here. And these are like design conditions. It's those are actually like standard design conditions, right? So let's just move on to the calculation. You can see here that see the BTU that we got before, the 4,000 and the 10,000, almost 11,000, and then the CFM too. And if you notice, this cooling is made up of both sensible and latent cooling. Sensible cooling is based on sensible based on actual temperature change, right? And then latent cooling usually has to do with humidity. There's this thing called evaporative cooling where the humidity of a space is moisture is introduced into that space and it helps to bring down the temperature. And also, so that just basically means that there are some cases where, depending on like the amount of sources of moisture, it can affect the amount of heating or cooling required in that space. So that is the whole point of what latent cooling does. Okay, so moving on, see the total wall area, because we have to add like wall areas that time, the length and the height too. So that's how this was gotten. Now you can see the graph showing the heating and the cooling. This heating and cooling just basically means that it's going to do more cooling than heating. So it means there's more sources of heat which will be cooled. So the cooling load is greater than sources of cold. Okay. So let's go further and see what else we have. Okay. Now let's look at the heating load in details. So these are things that make up the heating loads, right? There's the windows where windows, there were no windows, right? There were no skylights. That's why they are zero. Infiltration has to do with air leaking into the space, and we selected that it was a semi-tight space. Then floors is usually by conduction, right? Depending on the climate, because the floor is not exposed to solar gains. Instead, it's like maybe depending on like the temperature of the ground temperature, and then how insulated the ground is, that will allow heat to seep in or out of the building. Then the doors too, because of the opening and closing, and then the insulation of the doors too. That is what affects the amount of the heat that is being lost through these spaces. Ceilings too, heat is being lost to the atmosphere from the ceilings, and then the walls. So if you notice, the one that has the greatest is the floor, right? And all of this information is already preloaded into manual J. So I mean, it could have gotten to have gotten all of these would have required like a lot of data being gathered to do all these calculations. But this already comes with like the design conditions and then the climate conditions of that space. So now over to the cooling load, you see that there's way more, right? So plants, who you think will not supply more, they supply. I know we had about 5 to 7 plants in that project. And this is like the total amount of heat that they release, although is very little and it's mostly latent because of the moisture. There's like a moisture relationship. Then occupants too. Occupants, that is the people in that space, they release both sensible and latent heat, because latent heat is like from when they're sweating and all that. Infiltration, same thing as here, right? So floors, appliances releases the highest amount of heat, or right. So that is why you need to like be extremely careful about selecting. And also in this now, because I mean all these calculations, you are not on site, they are just estimates based on what you expect. So this is not going to give us an idea that okay, these appliances are going to cost a lot too. So do we want to put in all these appliances or less appliances, so we can now like advise accordingly? there's even like a different type of calculations that goes with that, right? Where the building is checked to see whether it passes the energy compliance, yeah, to see whether the building is sustainable, right? So it's a combination of the amount of heat that the amount of energy that is in the space requires to function, and the amount of energy that can be lost or gained by that space due to the insulation or the envelope. Envelope refers to the walls and the floors and the ceiling, everything that's surrounding the building, basically. So let's just move on without spending too much time. Then you can see that it breaks down in details the information of the walls. Then okay, there were no below grade walls, no basement walls. Then we have the ceilings too. So we treated the ceilings of them as different ceilings with different areas, but still a one whole ceiling, right? Then there's no skylight. Doors, there was only one door, which was like the entrance door. There were more doors that have shown up here. Then floors, there's just one floor, but they are like treating it as different floors for the different spaces, conditioned spaces. Windows, no windows. We didn't take ventilation into consideration in this case, but in some cases we would have to. And usually, the bigger the building or the more commercial the building, the more we put ventilation into consideration. And when I say commercial, I'm referring to generally building that is not residential, right? It could be a public building, it could be an industrial building, right? So these are all different categories, right? And there are various reasons why they would need that. Then hot water piping, this varies, right? It could either be the type of hot water piping is basically just the either the hot water that has to run through the house, right? And that also adds to the heating because some type of HVAC equipment requires like hydronics where like pipes or tubes are laid in either the walls or the ground, and then water runs through them and then it releases radiant heat into the space. So none of that was used in this project. We didn't use ducts in this project as well. Then so that is just it was a very simple project. So it's just for learning purposes. So at least you get the concept so that when time comes you can apply it to other things. So occupants, yeah. We assume this. Although this, right? I know that I initially said that it's supposed to be two occupants, right? So each of the occupants produces an average of 200 per person. So there was a slight mistake where I was specifying one occupant per space, which is not the case. That is not how it should be, right? So instead, you only specify occupants for like the living room or the bedroom because that same person is the one that's moving around. So there's not like multiple people. So, but this is still a little bit insignificant, but just something to note. Okay. Appliances. You see, like this is why appliances had so much heat being released, and the one with the highest is dishwasher. You see, refrigerator. They release so much heat because of their due to their operation. And then you have light fixtures. The total of the light fixtures. This. Then you see that this is also even talking about the spaces one after the other. The bedroom, the living room, and so on and so forth. And each of them has their like little load calculations. Right. And if you notice that kitchen, there's a lot of gap between the cooling load and the heating load. That just goes to show you that the fact that the kitchen is used for cooking, which is like a high heat producer, and also all the other equipment that are placed in the kitchen is what makes this cooling load so high. So moving on. Okay, that's pretty much it. And then we saw the summary above where we saw the heating and total heating and cooling here. Right. So let's just go on to the project for today, which is manual N. We're going to be doing manual N calculations for A. different type of building. So we're going to be looking at this building. Let's go to the beginning of the oh shit. Okay, let's go to the beginning of this project that we're going to be working on. So this is what the file should look like. This building is based in California. Yeah. And this is what your project file usually that they will send to you should look like. That is, the architect has already worked on it and has put in like some information which you're going to continue working with, right? So let's quickly scan through like what the building entails. It is a winery and vineyard building. Right, it is a very big building. So this is the floor plan. It has a storage. This is the ground storage area or the ground floor. That has this is the 5,898 square feet is the floor area of the ground floor, and it extends, it covers the entire space, right? And there's a door here. You can see door here. Then these are just like barrels, right? And this is another overhead door. You can see the doors have tags, right? And then there's another smaller door. These doors are should mostly be for equipment and maybe machinery. Then this one is for like people to pass. And rightfully so, the architect also gave us okay, there's another door here too. So now this is the next floor, right? Okay, this has a mezzanine floor, right? And then this is still part of the building. And then we see here that we have information on the building. So there's the wall. Then you have two types of wall. They are both stored walls. And then anyway, this is an external wall, as you can see here. Then these are like the different door types that we have available and their dimensions. We're going to need this when we are filling information for manual N. Then the windows too. There are some windows too with their dimension. Let's go on to see where the windows are located. So, and then these are those information to help us understand the project, right? So let's go to the next page. Right. So okay, this is just a lighting plan, reflected lighting plan. It's a lighting plan. Okay, so we don't need it. This is electrical. This is the roof plan. Again, we don't need this. I mean, if we were going to like place equipment on the roof when the attic would have needed this, but for now we don't. Now this is what the building looks like. This is the north elevation, right? So you can see the building starts at ground grade and then it's as tall as this is where the ceiling is 27 feet, and then the roof, top of the roof is at 39 feet. I have to tell you how large this building is. It's a kind of a warehouse and it's a production building, so that is why it's so large. And then this is our main entrance door. This is the south elevation. So the architect has helped us a lot in giving us these directions or these orientations. Let's go to the next page. Now this is the side elevation, which is the east. Okay, now we have windows here. So 1, 2, 3, 4, 5 windows. They are like at the top of the building for ventilation and for like basically windows, what windows do. So these are like the extra doors we have here. So there's one door here too. So let's just study the project and see what we can come up with here. Okay, what do we have here? Okay, this information on the roofing and the panel. This panel is just like the exterior finish of these walls. So next page. So these are like sections. This gives us an idea of what inside the building looks like, right? So you can see that there's a floor inside Then you can see the type of roof that we have here and the type of ceiling. This building does not have the usual type of ceiling where it is covered on the inside. So this is just trusses. So it's like this piece is exposed, right? And then if you look close, you see that the roof has this refers to insulation, right? And the walls too. Although the walls actually have thicker insulations because the walls are supposed to also carry the load of the building. So next page. Okay, this is the windows. This is like still a section cut. So still you are looking at the building from the inside now. So that's why as if you're seeing these windows in two places. So it's not as if it's the two sides. So next page. Okay, this is information on the details. And then here we can see the exterior wall. We're going to need this information. We have the type of insulation, it's air gap, it's a metal structure, then insulation here. So this is just going to give us an idea of the type of building. And then other information too that we might need. Okay, this is the door. Okay, and then this is basically the structural information that we don't need all of. Okay, this is the foundation. Yeah, this is the floor. So you can have an idea if it's insulated. If it was insulated, they would have placed information on that here, but it's not. Okay, so this is the final page. So let's go into the manual N of this particular building. So for manual N, yeah, we are going to use an Excel file. So this is an Excel file straight from ACCA, and it came preloaded with information just like the website for manual J, but it can be accessed offline, and then it is also locked, so you cannot edit some information. The parts in yellow are editable. So this is the project name, which I've already filled in, right? And then this is the location. If you notice, there's some similarities and some differences between manual N and manual J. So this is the location. Then let's see. Don't like this. Okay, so let's open this fully, right? So yeah, this is the particular cities, because you to know this, you have the address given to you, right? So that will also help you to design accordingly. Then this is the city, right? And then the zone too. Okay, this basically means is asking how you want to do it, right? You have to do it by block, by zone. I know we talked about space by space or room by room or zone. We also talk about zoning, right? So this is how we want to do it for this building. So let's take block. So now remember that the floor area was 5,898. That's what we have filled in already. I already filled it in so that we can spend less time. And then to get this AG volume, this is just the total volume of the space. Remember that it was 39 feet, right? 39 feet. Now this building has a funny shape, right? If you look at the roof plan, you can see that there's a wall going straight down. This is all around it, right? This broken line is a sign of a wall under the roof. You can see more wall under the roof, right? Even though the side view of the building doesn't look, it's not straight, but there's a wall that goes down here, right? The wall goes down here, so that wall is straight vertical. So now we are going to do some estimation, right? We're going to take that this space. I used 39 feet as the height of this building. If it was the ceiling, if it had a ceiling, right? Oh shit. If it had a ceiling here, I would have taken that as the height of the building, because ceilings are like what separates it from the roof. But being that everything is open to the top, I'm taking it that the whole building is conditioned as one whole large space. That's why I took 39 as the entire height of this building. And also because I know that it's just this part that is getting to 39, but I'm going to assume that this space here, this triangle that is cut out here, which is still part of the envelope, is going to take up this space and this space. So that is giving us an estimate that this is a rectangular cross section having a height of 39 feet, right? And then the walls all around. So that is just an estimate on my part. I mean, after all, everything is estimates. Only that it is estimated, it is calculated estimates, and it's like reasonable guesses that we're doing. So go back to this. So now, where's my calculator? I took that height and multiplied by 39, the floor area, and then I got this. So that is my area of this piece, right? So now there's a lot of other information. Let's go over it one after the other. So these are like design conditions for this piece. There's the humidity, there's the cooling design. The cooling design speeds dry bulb temperature, and the heating speeds dry bulb temperature. So I mentioned one time that when you are designers, you are designing rather. So design is not just about putting circles or putting shapes on a paper. Design in terms of engineering is setting the conditions of a space, of an element or of a thing to meet certain conditions and to function properly, right, in what it is supposed to do. So when you're designing the HVAC system for this building, you are designing it so that it is comfortable for people to stay in it and for the work that's supposed to be done there to be done properly. So that's how we have design conditions, which is this, right? So assignment is for you to go and look at why this information is like this. I'm not going to explain it in this class, right? So now let's scan through what manual N is all about. So when you get this document, you just scan through this information, read through it. It helps you understand how to use this, right? Now there's form 1, and then there's the database. So this database is basically, if you notice, is in yellow, and the yellow part is the part that you can edit. So this is already some preloaded information that is on the types of glass that is used in the project or can be used in the project. Then skylights if necessary. There's information on it. There's the doors, types of doors that can be used. There is some come with the original Excel file, but some, as over time, as you use, you get doors that are not in this database, and then you add it manually here. So when you add it manually here, it comes up under your options, right? So like this, now this overhead door, I added it because in this project there's an overhead door. So next, which is like a garage door. Then this is also wall data, then ceilings data, right? Then this is the floors too, data on the floors. So just keep going and going. So that is the end here. So now let's go back to form 1. This is where everything meets, everything comes together. This is like your final, what your final document should look like, right? So if you also notice, this is the design month, this is the design day. Yeah, basically it's trying to like estimate for the amount of heating or cooling that building will need. And this design month is like the peak period in the year where it's expected that the equipment you're selecting is supposed to perform at its maximum, right? So it designs with that in mind so that when the other less demanding times come, the equipment can still function, right? So now let's go over it one after the other. So now all this information, let me show you how I fill them in here. See that they're not in yellow, so you can't edit anything here, right? So now let's go one after the other to the different tabs. So glass. So we had 5 windows, right? Let's go back to that. This is our okay, 5 windows on just one side of that building. Okay, this is it. So now this west does not have any windows, only the east has windows. This is 1, 2, 3, 4, 5, right? I remember that we had dimensions for these windows. Yeah, under here, dimensions for these windows, for the windows rather. 10 in width, 3 in height. So we don't have to measure anything. So let's go back to manual N, right? And it's on the east. If you remember correctly, it's on the east. And this is the quantity of windows. This is the direction it is on. Then the width and the height. And then, like I said, usually designed with the mindset that it should be the worst case scenario. So this shading is just gives an idea of how well that glass is protected from like solar radiation, right? So we're going to assume that there's no such thing, right? Okay, so let's move on. Then this medium, when in doubt, just take medium, right? But if you have information on the building, the construction width of the glass, you know what to do. So now you can see also this what we selected here, right? Okay, this is like a list of the type of windows that are available, right? So this is metal no break, and this is basically it's either a fixed window or an operable window. Those are the two options. Or if you had gone to database, if you have a different type of window, you could have gone here and put it in something that does not fit into any of these categories, right? But I'm going to go with fixed search because I don't think those windows are operable, yeah, because they're just up there and they're out of reach, so they can't be operable, right? So now whatever you select here will reflect here as well. This is for you to like fill in extra information. So now there is the overhang and there's the top of the overhang. So they also give you like information what it looks like. Right, so this X, the distance the roof extends out of the building, and then the distance to the roof to the window. Let's look at that once again. Page. Okay, so you can't always get the calculations right, but you can make good guesses. So this is 27. This is where the window is at. We can't really get anything on how the distance is, right? But we can take a standard value which has been put in here already. So this is usually what like is if when you don't know you can always look up these things and get like an average standard value. So the X is usually about 1 feet and 6 inches, and it could be longer or it could be shorter depending on the height of the building. And then Y, which is the height to the window, is about 10 inches. See, there's nothing here, so it's not up to a foot. So let's go on to the next page. This is all for the glass page. Basically, this glass page is just to fill in information on anything at all on the envelope that has a glass. It could also be a sliding door that has a glass, like it's mainly glass, right? But the only thing we have is just the window. So let's move on. So in this project, we don't have any skylights. Skylights are lights in the roof that are letting sun. So you see that from beginning to end, there's no light in this. You come across projects where you have lights in the roof. Not even when I mean lights, it's not as if it's LED or electric lights. It's just they are like windows in the roof that permit light into the building from the sky, basically. So let's continue. There's no information on that. So let's move on to doors. Right. So now we have 3 different types of doors in this project, right? So there's the overhead door, which you can see here. Let's find it. Let's find that door. Let's go to the floor plan. I'll find that door. Right. This is it. Here's the floor plan. So this is an overhead door. So you can see it here. 2 is referring back to this number 2 here, which means overhead rolling door. And you have the information 9 by 10. Then we have a commercial door 3 by 7. Commercial door is a regular door, right? You see it here. This door here, and that's number 1 for people to like walk in and out. Then we have another door which is a barn door 12 by 14, which is a very large door and is here, right? So this is almost like a farmhouse, right? This is what this is for. This is it here, 3. So now let's add all this information into our manual N. So now if you notice this we have that. Okay, let's just take it one after one at a time. So we have on the south elevation, the west elevation. Let's have the west elevation. On the west elevation, what do we have on the west elevation? Okay, okay, let's see. This is the north and south, right? Okay, let's see south since we're already here. South elevation, we just have this large door, which is 12 by 14. And we put 12 by 14 here. 12 times 14, that is 168. Right, this is what I got from the door schedule. So on the south, I already filled in this information 168 because we need. I suppose, unlike the window where we have to fill in width and height, this one we just fill in the area one time. So on the south, we have this door. On the west, what do we have on the west? Right, so west and east is what we have next. On the west, which is this is the east. Okay, on the east we have just this single door, this single small door. So let's see what we did on the east, just this single door of 21, right? And then on the west, which is the first, let's go back and see what we have on the west, right? This is the west. So on the west we have this small door, which is 21 feet. Then we have this overhead door rather, which was, well, is it 7 by, let's look for it. Okay, this is it. That commercial, sorry, the barn door, no, the overhead door rather, 9 by 10. So now I just added it up. So I took the 9 by 10, and since they're all on the same face, and we from the way manor n is structured, or the way this form is structured rather, you don't have multiple, you can't fit in multiple doors in one place. So you just add them up together, right? So that's why in the west we just took the addition of the existing door, which is 21 plus 9 by 10, 90, right? And so, okay, let's do that. So we have that small door, which is 21 plus the other door is 9 by 10, which is 90, 9 by 10, which is 90, which is 111. There must be a reason why I might have. Okay, I got one. Okay, you see that on this page there are actually two doors. This tent almost kept my attention. So there's another door here, which is the same size as this one, right? So that means 21 into two places. So we add 21 to our existing information because you missed that at first. Okay, that's how we got 132. So 132 for the total areas of doors on the west, right? So we are done here. Okay, let's look at the different types of doors available. So we have a metal door and we have a wooden door here. So this overhead door is already preset, right? And then taking that the other two doors are metal doors because I always like to specify external doors as metal doors for safety and security reasons, right? So and these are the two options we have. I mean, if your architectural file comes in or your project folder or file comes in and then there's extra information on the type of doors, you can go to your database and then let's go to database and see under the doors. Yeah, you see these are the only two doors we have here. You can now come here, give it a name or a code, fill in like a name you want for the description, and then set in the U value. The U value is a way is a measure of the insulation and capacity of the material used for the door. And when if you have a full file, you would have all that information, or you can always look it up if you have like some information. So let's continue. We are done with the door tab. Let's go on to the wall tab. So yeah, this wall tab, I had to input it manually myself. Go to database, wall, right? These were the available walls from here. You see that they have their own constant numbers. So I had to and these walls that I saw in this project, I've never seen this type of walls before. So I had to set the information myself. I had to name it and fill in information on it, right? So let's go back to the walls. So, and then also how I got this is just basically the length of the wall, the height of the wall rather, times the length of the wall. So let's do for each of them and see. So for the east wall, for example, right, the west wall, let's see. Hopefully we have, okay, we should have information on the length of this wall. Oh, sadly we don't, at least not here. Can we get that here? Okay. Okay, we have our information on the wall length. So this is the floor plan, and you see that this is the entire length of the wall that we need. That is the longer side of the wall, which is turns out to be 126. That is such a large distance. That would have been 50. What does this 50 mean? Let's see. Okay, the 50 is like from this place to somewhere here. All we need is the entire distance, which is from here to the end, and all we have here is 126 feet. So now 126. So we'll multiply that by the height. Okay, so for the longer part of the walls, if you notice, we have that this is where the wall stops. So I'm going to take this as the height of the longer walls, which is 27.5, 27 feet 5 inches. So we calculate 27.433. Let me confirm that that is the actual. Okay, let's first of all do 5/12 and see the decimal of that. Okay, 0.4166. Okay, so when that means for this 27, it will be 27.4166 as the height. Okay, 27.416 times the length of the beam of that wall. Remember, it was 126 feet. Okay, equals, and that is 3,454 for that wall. For this wall, this is the east wall. Okay, this is the height we got, and then this is the length of that wall. Okay, so now let's check. That means both the east and west wall will have this as their height, as their area rather. Right, so we fill it in for the west wall, and the east wall is going to be the exact same height because it's the same width, the same length and height too, so it will give the same area, 3454. So now let's measure for the south and the north walls, which should be the same thing too. Okay, so okay, we can't get it from here. Okay, let's go back to that floor plan. The floor plan tells us that this wall is this long. Okay, you see that extra length is what we have here, right? So we're going to just use, okay, let's see whether we can get it from up here. Oh, perfect. So we're going to just take from here because this is probably there for aesthetic or extra reasons, but we just need the part of the wall that is insulated, the part of the wall that actually covers the envelope. So you see that from here to here is 50 feet, and that's what we need. 50 by 50 feet is the length, and then the height is what? Let's look for that. Okay, 50, and then we are going to take 39, right? 50 by 39. 39. Well, in this case now we can make up for that extra length of this, so let's assume a lesser value. So if this is 50 and this is 39, so let's take some, and then this is 27 too, 27 feet. So 27 to 39 is 12 feet, right? So means this to here is 12 feet. So let's take half of that distance. which should be closer down, because we want to assume that this is a rectangular wall, right? So if taking this as the height would mean that the wall extends all to here, but that's not the case. So let's take half of it, because if you divide this space into two like this is about a triangle that makes half of this rectangle. So if you take half, it should give us like as accurately as possible. So half of this height is 6 feet, because this is 12 feet. So 6 feet, add 6 feet to 27, or just take away 6 feet from 39 to, so that'll be 33. Then the 2 over 12 is, okay, 0 0.166, so that'll be 0.166, so that'll be 33.1. Okay, no, that is not correct. 33.166, yeah, which is the height, times 50, which is the length of that wall. Okay, 1658. Let's go to our file and fill it in. 1658, and it's the same for the next two. 1658, right, for the north and south walls. So now partition walls is for any internal walls that we have in this space, right? But in this project we don't have any internal walls, because it's just one large space, like from the entire ground area is just one large space, right? So we don't have any partition walls for this, right? But if we did, we would have selected the type of material it is. You see that this wall is also under the list of walls, so we would have checked what material that wall is made of. Usually internal walls have less insulation, or are usually slightly thinner than external walls, because they don't have to protect against external factors, and they don't also have to carry weight, the load. They are not load bearing walls. So thankfully we don't have such, but if we did, we have just selected one of the walls, and then to get the total square, the total area of the walls, there's no space to start putting it one after the other, because most of the interior walls are a lot, right? So let's look for a project where we have interior walls and see how we can find our way around. So this is a project where we have interior walls, and it's also a commercial building too. So if we had to measure for the interior walls in this space, we are just simply taking these lengths and then started measuring the walls one after the other. So this is 105. I need to edit these dimensions. So theme style, so modify. So it shouldn't be decimal, it should be architectural, and then it should have this. So it should give us the feet and inches. Okay, those. So let's try that again. So just come here. Okay, this turned off when we did that, so we turn the snap back on, so it's easier to snap to the locations that we want. So come here. That is better. That is 8 feet and 8 inches. So just do that and then measure the entire length. We measure this. Is 5 feet 6 inches. So just measure and I keep adding it up. So add that 8 plus 5 plus the rest of the length. This has a lot of walls, unfortunately, right? But basically, this is just going to be treated. It will be treated like one large wall or one long wall that is just within this space. So Manual N doesn't really permit you to start filling it. Imagine having to fill information on this one after the other. So you get the entire length and then multiply by the height of that building. or the height of the walls. And in this case, this building is a small building, so it's not as tall as that 39 feet. So about 8 or 9 feet should be the height of this building. Okay, so go back to this. So, but thankfully, we don't have any internal walls, so we just delete. So then research on what these two means, and let's go on to the next page. Ceilings. So now we remember that we don't have any ceilings in this our building. It's just open to the trusses. These are the trusses, the structural members that hold up the roof. So there's no ceiling. Ceiling is like something that has like a separate insulation value. So that's what our roof has instead, right? So for roof ceilings, we could have selected any of these ceilings here. Okay, let's see the one that best suits. Okay, we have information for that. Right, we have information for that. Okay, confirm. Okay, metal deck, no ceiling. Then there's a ceiling board. We don't have that. We don't have this. Then ceiling below roof dress. We don't have this. So this is the closest what we have, right? So metal deck plus, okay, that metal deck is just basically the metal on top of the roof. And then, okay, this means there's a board, but we don't have that. So it means we don't have any board. We have no board. What we have is just the roof, right? So in this case, we don't have any ceilings. Okay. But let's just assume we have that as the ceiling because that's the closest to match. Now this is going to bring us to next, which is the floors. So these are the different types of floors available, and we select the one that best suits our building. So over enclosed space, no. Lightweight over open space, no. These are basically just when the building is built above like a basement or like an open space, but that's not the case in this building. Commercial over, no. Basement, there's no basement, it's just from the grade up, right? So this is the best slab on grade, right? And let's look at that building, right? You can see here that this perfect. So this is the grade, which is the ground, and then this is the foundation of the building. So you just built on the slab. This is the slab. So this is the perfect floor for this building. And now we have options of does it have insulation or not. We are going to assume worst case scenario and then select that it doesn't have insulation, unless our file tells us that it does. Because the whole point of this, we are trying to get the amount of cooling or heating needed for this space. So if we assume that there's insulation and then there ends up being no insulation on site, means our entire calculation is going to be null and void, because whatever sizing we do is not going to work for that space, because if the building is not insulated, the floor is not insulated, it's not going to work. So we're going to assume that it is not insulated, which is the worst case. Now in case it is insulated then it still falls under the range that we are going to get, calculation we're going to get from here. And then the perimeter, this is different from area. Perimeter is just basically length plus breadth plus breadth. It's just the distance around that space, right? Because that is around that distance, that is where the external air interacts with that space, right? So let's see. So we've gotten it as 120. We got our floor from that floor plan. We're able to get that it is 120 here and then 50 here. So 120 plus 50 is 170 plus 50. Okay, 170 plus another 170 because there's length and breadth twice. Okay, 340. So that is this length, this breadth, this length, this breadth, and this length, right? Okay. Oh, there's something I skipped. Let's look closely at the wall information, because I already I already like put it in, so I already did not look. Okay, so this is This is this information I used to create that wall I put there. You see the 25 baht, which is insulation, the arrow value. Then we have that is the exterior is metal. Some cases for like some buildings it could be a wooden panel, but it's a metal panel, right? And it's a metal structure too. So it's also a stud wall, but is the stud is metal, not wooden studs. Okay. Then 8-inch gap. This serves as the cavity insulation. Then this manufacturer structural. Okay. Okay, so that is pretty much all the information we have from architectural file. Let's look at the manual. And when I was filling in the database, the walls. So this is that wall, is a frame wall, which is a stud wall, metal studs, which is the R25, which is the insulation, wood sheeting, right? And then siding. Good. This is not supposed to be wood sheeting though. It's supposed to be metal sheeting. So it's a mistake on my part. But I don't want to. I hope this editing does not affect other places. So it's metal. No, sheeting. Let's leave it as wood. Let's confirm what sheeting means. Let's confirm. Let's go to. Okay. No. Okay. When as a designer, you're going to be doing a lot of research yourself. So let's look see what wood sheeting looks like. Oh, there's no internet. Internet right now. But you can just always confirm from the end what wood sheeting looks like and decide if I've done the wrong thing or not. Right? So let's move on. So after I did that, I was able to like also calculate my U value factors. I was able to look it up based on the information I had on the walls. Let's move on. We've done floors. Now internal loads. Okay. Right. So let's see what needs to be changed here and then change it. So we have lighting fixtures. I'm guessing they are 24. But let's look at the reflected light plan. Luckily, we have that in this plan, right? The reflected light plan. Reflected light plan is basically just what the way the architects feels the lighting should be arranged. So let's calculate. 1, 2, 3, 4. Okay, I'm counting. 3, 3. That's 8. 3, 3. That's 8. So 8 times 3. There are 3 rows, which is 24. So that's correct. That's correct. So that's 24. 24 light points. 24 light points, and then we are taking that each of them is 20. Well, let's confirm. We can't just let's borrow information from our manual G. We have some information on the lights, right? Lighting fixtures. Okay, appliances. We have to go down to appliances. We need the BTU information. Oh, this is actually going to be in BTU, so it's not going to be the same thing, right? Okay, yeah. The average they are using 100 watts, right? 100 watts. Okay, let's keep it as 100 watts. Now this will obviously be a source of heat because there will be a lot of heat released from this 400 watts bulbs, right? What is this? Okay, that is not necessary. Okay, now we are assuming that there are 20 people working. That's such a large space, so I'm assuming that they're going to be treating the individuals working there, and there's a category of the kind of activity you're doing. So this this is for like mostly commercial buildings. So these are the type of activities on average that can be. So you just take the one that best suits what is going to be happening there. So it's a warehouse stroke, factory stroke, farmhouse kind of building. So they will not just be standing, it can't be light work, right? So they'll be standing and it's not just some movement. Some movement is better if it's like maybe an auditorium, right? So now I'm expecting that people are there going to be factory workers there. So I'm expecting that at least majority of them will be doing some movement and lifting, which is what I've selected here. And this is also going to affect the amount of heat that they produce as they work, which is going to add to the heat being produced inside that space, and that is going to increase the cooling load. So now next is office equipment. So forget this office, it's just basically any type of equipment here. So I'm taking that there are 5 large equipments that each of them has 250 watts, right? Or we can add to that 250 watts, 250 watts. That is too little. Let's keep it at 400, right? 400 watts each. If we had more information, we would have been able to fill it more accurately, but we don't. So 5 large, and from what we have here is mostly a storage space. So there's not a lot of normally if it was a full blown factory, there's supposed to be more equipment, but this just looks like a storage space, barrier storage, right, and production area. So there's not going to be so many equipment here. So I'm just taking this as an estimate value, right? Then food service. This is if it was a commercial kitchen or restaurant kind of space. So we don't need information here. We don't need this. Although, actually, this is where our information fits in better. The one we put here, this is where it fits in better because it's actually, from what you see, is a winery and vineyard building. So it's likely that that is what. So this will be deleted because we don't need. It's not an office space by any standards. Then we have plants. Just take plants usually produce very little. It's very, very insignificant. So even if and then it's a factory space, so it's unlikely that they're going to have so many plants. Or they might, because they may need to like absorb carbon monoxide that is being released, right? So let's leave it at this, right? So this we don't need to make any changes here. Okay. So there is what they call a draw through fan and a blow through fan. So please research on it and then so that when you are doing your own manual and you'll be able to like fill in the value correctly. So I'm not going to say why I put this in here. Let's go on to the next page, which is the docs. Good, good. So I know that in the manager I did it was a ductless system, but this is ducted. And for ducted, you need duct insulation because the air is going to travel through the ducts round, right? And but there's a minimum of 6 R6. You come across a lot of R and U when you are referring to anything that has to do with insulation, right? So please research on what R values are, R values and U values, but they are both a measure of insulation of a particular material or a particular item. So let's see, semi-tight. When in doubt, pick an average value, right? So let's take average, right? Now, as we do all these little changes now, we would see that the on the form, which is our final form, the values here will be changing. But if they've not all changed because there are some things we've not yet filled in yet, right? So let's continue. So we have RSS, which is the minimum insulation value, and then we have these default values here, right? This change with location, obviously, and but for this project, we're using these values, right? So for another project, these values are going to change. So you read up on why they change and how they change, right? So now we have still on this page semi-tight. Let's leave it as semi-tight, right? And then this is supposed to be the length of the duct because it's supposed to be a ductless system. If it was ductless, I could have left it as 1 because these values can't be empty. I left it as 1 foot. This is in foot, the length. So I left it as 1, but this is going to be ducted. So I want it to be ducted because basically for a large space like this, ductless units would struggle in conditioning this space. So it's better we have like ducted systems to be able to like drop it to registers at different spots, right? So now let's assume that I'm going to have 20 feet of 20 feet is a lot, right? Let's say 10 feet. 10 feet. Okay, let's just put 15 feet of no, 15 feet. That is a very large space. So 20 feet is fine. 20 feet, 20 feet, right? Now let's, and also as you're also making edits here, it's good to also be looking at your form to ensure that their things are panning out fine. So you see that there's a problem here. There's some information that was not done properly, and it looks like it's from here, right? So let's go back to ceilings and see what could have been the problem. Oh, you see, we selected a ceiling, but we didn't fit in the footage, the area. So the ceiling area is usually the same as the floor area, which is 5898. So ceiling 5898. If you remember, we also did this in our manual G, ceiling and floor default, right? Because we don't have the information on the ceiling. Let's go back to form 1 and see. Okay, values are taking shape now. We're almost done actually. Because we're almost done. So we are going to see some heating and cooling loads, right? So let's go back to, we've already looked at internal loads, right? And now we look at dogs. We've already looked at this, right? And if you notice, this changes when you change this information here, it affects this amount of heat here, because it's expected that as air travels through the ducts, depending on the length, the distance of the air travel, some heat is lost and some is gained. So it's still part of the heat loads, the cooling and heating loads too. Okay, so that is ducts. Now let's continue. We still have to deal with infiltration and ventilation tabs. So infiltration basically refers to when air leaks through the building, like those gaps in the windows or in the walls, little small holes, some are not even visible, right? And then as people open the door and close the door, so basically anything that has to do with air leaving or entering without, like, you didn't want it to leave due to like little openings, that's what infiltration covers. So it is not intentional. Air exchange that is not intentional, right? So now it is a single story. We have options of multi-level. There's no multi-level in this building. It's just one story. Despite it's a very large building, or tall building rather. So how many exposures? We have more than one or two exposures. We have 3 or 4, right? And then we are taking that the tightness of those is semi-tight, right? Okay. Then we also have the types of doors. Remember, we had 2 types of doors there. 2 types of doors. One of them is a single swinging door, and the other is a double swinging door. Let's look at this again. Okay, let's look at the front view. Okay, this is a double swinging door, as you can see here. So this will swing in, this one will swing in, or in or out, basically just a larger area door, right? So we already have this as a single swinging door. We have 2 of it, but we'll just take for 1, because we are not assuming that 2 of them can be open at the same time. This is just trying to understand what the activity in that building looks like, right? And this TR refers to verb exit space, or how many times the door is opened. So these are different depending on how much it is opened. I mean, if it's like a restaurant, it's going to be opened a lot of times per hour. But this is a factory or a warehouse space or a production space. So most times, somebody that comes in would not likely go out for a while. So the number of times that this building will be opened, or these doors are opened, is very few per hour. So that's why I selected the lowest value. Same thing with this door. Once like workers have come in the morning, which is the time the door will be swung a lot. But after then, there's not much swinging per hour. So I selected as lower value too, right? So let's see, do we need to add another? Right. And also check what vestibule means. Vestibule, because that also affects the amount of air, heat that can be lost or gained when the swinging takes place, right? So moving on, So we've just put in our existing doors into these categories. And remember, it's only doors that interact with the outside, because those are the doors that affect the heating and cooling, right? So RPM. I don't think we need any information on RPM. No, we don't. Okay. So significant overhead. This is for I was wondering why we did not fill information for the overhead door. This is that for information for it, because it's in a different category altogether, right? So remember that the area was 10 by 9, so that is what we fill in here. And then this, we still selected an average value of 6, which is close to this. And obviously, because of the nature of the door, it's not going to be opened a lot of times. It will be open only when necessary. Maybe if there's need to bring in equipment or something of that nature, or bring in a machine, so it won't be open. In fact, we can even reduce this, right? Still per hour, right? So let's move on. We are done with infiltration information. Let's go on to ventilation. So ventilation, I've spoken about ventilation when we're talking about the notes, right? So ventilation is a bit tricky, but not entirely. It's something that might a bit you I mentioned about ASHRAE and how they have some limits or some standards as to the amount of air that can be let in or out of a building, right? Or not let in or out, that's infiltration. Amount of air that must be put into a building based on the nature of the building. So most times in commercial buildings or industrial buildings, which this is, it is those values are usually more strictly followed. So let's go over to, I already looked up. Oh yes, perfect. Despite me not having internet, this page is still loaded. So I went to the 2024 International Mechanical Code, IMC 2024, and we find this table. It gives us the minimum ventilation rate of buildings, right? Depending on the nature or the classification of the building. So this our building in particular has um okay, let's see which it best suits. So none of these, none of these, none of these. Sports amusement, storage. It's similar to this, but not entirely, because it is like a food processing kind of building, because it does is a winery, so it's likely for wine production, and it's not exactly a warehouse. So it's partly warehouse, but it's still for production too. So let's look for something that okay, manufacturing where hazardous materials are not used. So I feel like this is the one that most that this building most closely identifies with, right? So these are like different values. But let's just before we continue, let's just okay. So let's see. So it seems we've been looking at like an older version of that building plan. So okay. Apparently, the more updated version of that building plan has something which is a mezzanine floor. At that mezzanine floor, you can see there's a staircase right up to the mezzanine floor, and the mezzanine floor has is like a kitchen. You can see kitchen equipment here. This like gas cooker, or it's called a range. Then this looks like an oven or something for cooking basically. But thankfully, it's not a lot of kitchen equipment in this space. Let's look at everything else. So everything else remains the same, right? Okay, everything else remains the same. Okay, this is the main floor plan. So let's see the height of, okay. Oh, you see there's a little bit of change in this more recent file. Then you see the windows. Okay, this one that just showed more clearly as having glass. Okay, this is a section now. This section called section 2. And basically to find these sections, if you notice sections from here, you can, okay, not here, from the floor plan, you can see where sections are cut. Okay, it's not indicated here. Okay, this is not the main floor plan. Let's look for the floor plan. Okay, yes, This is the floor plan. This shows that there's an architectural section cut along here. So imagine a knife cutting this building here. So we'll now be able to see inside of this part and this part too. So let's go back and look at it. Right, okay. This is that section cut, right? So you remember that it was at too close to the edge where we have this mezzanine floor. A mezzanine floor is like a half floor. Read up what a mezzanine floor is. So this is a mezzanine floor, and you see that the content of the okay, this is like a cabinet. So thankfully there's like information on what it then this is sink, and then this is like a range. Good, 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 good. All right, so let's go back to that first page or the main floor plan. Okay, so you see this is the mezzanine floor. Mezzanine floor is just, but then again there's no wall per se here. It's just an open space with railings. There's information about these railings. Let's see where we can find that information. There's no wall separating that, so it means it's just okay. Good. This is it. This is the side view. This is another section on the side. So this is the entire floor area, and then this is the mezzanine floor. It's just a small section that is at one end of the building. And if you see, we would have expected a wall, but there's no wall. So that means it is still treating this whole space as one uniform space. The only time we can treat it as different spaces is if there's like a wall separating. So I mean the air is uniform around here. So any condition we are doing is treating this as one space, which is one zone two, right? So now let's go back to that this thing. So it means we have two spaces here with slightly different um, um, conditioning, right? Because even though we don't want to, even though there's no wall here, there's no way the conditions down here will be the same conditions up here. So we still need to treat it like a separate space on its own to an extent. So that means still here we're going to look for. So we found this which suits the entire floor space. Now let's find something that suits that place that looks like a kitchen. So this is a kitchen, but this is for private dwelling, so we don't need this. So let's look for like a kitchen, but for something more commercial. Although, okay, this works. Okay, no, this doesn't work because this is a food and beverage service. This is for like large kitchens or like commercial kitchens, but that's not what we have here. Okay, let's keep searching. I found, okay. You just want a kitchen that closely represents that space. Okay, this is what we skipped, is not it? Okay, private dwelling. If you notice, okay, let's not talk about that. Kitchen, retail stores. I saw a kitchen here earlier. Okay, let's just take this. Well, this is the closest. Okay, let's just see. I believe a smaller kitchen or a residential kitchen might be better suited, right? But let's just take this kitchen, right? So that we can design accordingly, right? So we also have exhaust because our kitchen don't have exhaust too. So it's better to be on the safe side because my dilemma was choosing between the two types of kitchen. There is residential, then there's commercial. But I'm expecting that since this building is not a commercial type of kitchen cooking building, I'm not expecting so much demand on that kitchen. But it's still better to take this to be on the safe side because if for any reason the cooking they do there is more intense than residential cooking, that means my design is not going to be suitable right? So I'm going to take this commercial cooking, right? Commercial kitchen cooking and design based on it. So this is the ventilation. If let's look at these different headings, right? So this is the occupant density. This has to do with the number of people that are permitted to be in that space, right? Depending on what type of space is. You see there are different values, right? Per this is the number of occupants here in that space, right? The density, right? Per 1,000 square feet. Okay. So taking that the space is up to 1,000, like our own now has a space of about 5,000 plus. So that means this will be this value times about 5 or times 6 because it's close to 6,000, right? So per 1,000. Then next is these are like standards, right? Next is people outdoor air rate in breathing zone, so CFM per person. So this is the amount of outdoor air that's supposed to be entering that space per person, depending on the kind of space it is, the amount of outdoor air. Then next we have so this is usually, these are the units. This one is in number of people per 1,000 square feet. This is number of CFM per person. And if you notice, it changes too. So in some cases is less, when in cases where the place gets polluted easily or it gets contaminated easily, usually of higher value. Number of outdoor air that is expected. Outside air is usually called OSA, or ventilation rate, right? Then next we have rate in breathing zone. This one is per square foot. This one was per person, the amount of air per person, and it's also this one is per square foot. So the number of people there matter, and also the area or the size of that place matters too. So that's where this comes in. And then we have the exhaust. So this is the minimum exhaust that must leave that space. So in some cases it is not existent, but especially in cases where it the return air is is um is not contaminated or is still relatively fresh, can be reused or recycled, and like places where they do basic things, you can see some of these cases there's no need to specify exhaust for them. But in cases where it releases like bad air or contaminated air, there's high level of contamination like bathrooms, kitchens, and all these type of facilities, there's need. You can see this one even has a very high value compared to the rest. There's need, you see, there's need to change the air very much per square foot, per square foot. Now let's look at this, right? Okay, okay. Let's look at computing this information for this building, right? So if you notice, this rhymes some of these. So for that building now, see here that we have the production area and the barrier storage. We have the floor area. Then we have that mezzanine floor. Please look up what a mezzanine is. Right? I don't have time to like dwell on it now. And this is the area too. So if you notice, that mezzanine is like, it looks like a kitchen kind of space. So that is why I modeled it after a kitchen. Let's see that, look for that kitchen that we had here. Okay, this is it. You see 20, right? Okay, before we do this, let's just compare the headings and see the ones that match. That when I'm looking at it, you understand why. So this is basically, okay, right? This is density, which is this number of people per 1,000 square feet, which is what I have here. Then the next is people CFM per person, number of CFM required per person, which is what I have in this space. Now this, if you notice, is not here. I added this to my own table, although this table is gotten from this table. I added it to my table because it computes, it puts, this one is just a unit calculation, a unit value, but now we actually have the area of our space, right? So I'm going to take this, since this is per 1,000, right, and I have 1.5 here, So to get the actual number of occupants needed in this space, or that is minimum permitted in this space, I will typically take A times B, right? When I multiply my member dimension analysis, this is divided by square feet. So if you multiply by square feet, it cancels out and you're left with just the number of occupants, and that's how we have this. So we multiply by A by B, which is area by the density, and then we divide it by 1000. That's how I got this 30. Let's just do it briefly, quickly rather, so that it helps to understand better. So A times B, 1504, which is the area of my, times B. B is 20, 30,080 divided by 1000. If we divide 30,000 by 1000, okay, divided by 1000, okay, you have 30. It was 30,080, but the 80 was insignificant, so that's why I just left it at 30,000. So that's how we got 30 here. So now let's see how we got the remaining values. So we have, next is CFM per person. This is the rate of air that must come in per person. So now we have the number of persons here, right? But we are not going to use that for this. So we get that from this. This is, which is CFM per person, which is this column, right? And then which other column do we have here? This one is the CFM per area per square foot, which is this. Is this in our own table? And then this is now to get the required, because now we've put the density of people here. We've gotten the number of people that actually there based on the, because we had the area, we had the CFM per person, which are unit values, CFM per area, which is a unit value. Now we want to get the required outdoor air, right, based on this information we have, right? So we do D times C, which is D times C, right? So this is per person, this is occupants per person too. So by the time you cancel it out, the person cancel out the person, and then you come and see E times A. E times A is per square foot, and A is area. By the time you multiply, the area cancels out and you're left with just the CFM. So by the time you take the CFM per area and CFM per person, cancel out the per person and per area, you're left with just CFM. You add them up together and then you get this value, right? So I don't have a scientific calculator here, but let's see how we can quickly put that just for this mezzanine floor, right? So we read these values from here, and let's go there. Okay, now finally we have this required exhaust. The exhaust is gotten from this final column, where we just simply multiply this value by the area of that space, because you see this is divided by area. So multiply, we are left with just CFM, which gives us the required minimum exhaust that must leave that space. So now let's find that kitchen, because we model that mezzanine after a kitchen. Okay, this is it. This is it, right? This is it. Okay, so now let's confirm that the values match, right? Before we start doing any more calculations. So kitchen, that first column is 20. That's what we have here. This second column, we have to calculate ourselves, so it's not gotten from here, this column. So now next column is per person, which is 7.5, what we have here. Then the next column is 0.1, which is per square foot area, which is a unit value too. Now to get this total outside air required for this space that needs to enter this space, let's do the calculation quickly, right? So now let's calculate. Okay, let's calculate. Okay, now we're doing D times C plus E times E. D 7.5 times, okay, let's type it, 7.5 times D times C. C is 30. Okay, we can even use bracket. Let's use the bracket so that it's easier for us. Okay, AC cleared everything. So 7.5 times 30 C, right? You remember how we got C before? Times 30, close the bracket, plus, open the bracket again. This is E times A, which is 0 0.12, 0 0.12, right, times A. A is the area, which is 1504, as we got before. You can see it here, area 1504. Okay, times 1504. Close the bracket. Oh, 04. Ah, but it's still close. It's still close. 1504. There seems to be a problem somewhere, right? Okay. Okay, 405. Let's confirm that we've not made any mistake. Okay. So D times C, 7.5 times 30, plus E times A, 0.12 times A. A is the area 1504. So it's supposed to be actually 180, not 405. 180. 180. Okay. See, that's why I need to cross-check your work sometimes. Then, now to get this required exhaust, we simply go back to that original table. That last column, don't forget, is the last column, which is 0.7. So it was per square foot. So you multiply our existing square feet to get, multiply that 0.7, which we got here, 0.7, by our area, floor area, to get the value here. Let's confirm that. Right. So that's 1504. 504 times 0.7 equals to, and of course this only applies to spaces that require exhaust. There are some spaces that don't require exhaust, as we will later see. So you see 1052, which is approximately this. So now what are we modeling our ground floor after? Let's see. We found something, okay, which is this. Yes, this. Okay, right. If you notice now, we have 7, 10, 0.18, and then there's no exhaust in this case. So let's fill in our values accordingly. Right. So this. Okay. 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 7 is the first column, so it's supposed to be 7 here. Or I'm wondering why I have this. I must have modeled it after something else. Let's look for what I modeled it after. So I actually modeled it after this warehouse space. Right. Let's see. Okay, it's not even that. But this is 0.6. Okay, after the storage room, which has just this value 0.12. Let's see. So that's how we have 0.12 and 10. So this is not the case, because as you can see, this room it's not just storage, it's actually production area too. So that is not entirely accurate. And even though it might be, even though the building might be mostly for storage, we cannot take the lower estimate. So it's better to estimate as though it is for something more, which is where this works, where this suit falls into. So we have 7, 10. Okay, time is not really on our side, but you saw how I filled in the other values. 7 is the first column, so this should be 7, 7, 7. Then this 10 as 0.18. Let's see. Okay. Per occupant, this one will be A times B, which is this times this, times divided by 1000. Let me just quickly do that. So please confirm that your values meet my values. And you notice there's okay, we're supposed to do this. Let's do that quickly. So this is what the final values came to. So just check to ensure that your values match. And for this piece, there's no exhaust. Alright, so we didn't need to calculate anything for the exhaust calculation. So this is how to do your ventilation calculation for a space, right? And in some other buildings, some other commercial buildings, there are going to be way more spaces. So that's why you have something like this, where you have all the spaces specified and then fill in the areas and then do the calculations. You can always find whatever type of space it is here. So I think that's pretty much what we're going to be dwelling on today. So yes, let's get our final manual n value. So we've done all of this. That's the final page, right? Now let's go back to our form. Okay, you see that taking all that we put into consideration, these are the values that came out as a result, right? As they came out as a result. Oh, this looks like a problem, right? Okay. If you notice, all of them have slightly different values. It's because of, for example, the orientation. That changes a lot. The orientation changes a lot. If you notice the ceiling, you see that it loses a lot because it's directly facing the sun, so a lot of heat can be lost. So that's why there's a lot of sensible cooling because of that. And then there's a lot of sensible heat. And if you look at values that have very high values, you can trace it back to why. Then also look at infiltration. Because of the large amount of doors, see that the air tends to like infiltrate a lot into the space, and that's why we have such large loads here. And then we have our heating here as 206,000 BTU, and then our cooling as 87,000. And that cooling, there's both latent and sensible. So add them up together, getting about 104,000. So take this larger value and then we'll pick an equipment that meets. And now to get this, you just simply go to print. It's already set here. You do your print active sheet, set the paper type as sheet and print, and it gives you a PDF of what you've calculated so far. So now this will enable us select the number of tons that we need for the equipment for this building. So maybe in our subsequent classes, we're going to design for this building again, and then we'll decide how we're going to select the equipment we are using for this building. So thank you for joining in. Thank you for attending to this class, and I hope it was impactful to you. All right, bye.